So, first one. If you walk on a log that is floating in the water, the log moves backwards. Why is this so? Now, which of Newton's laws do you think would apply here? Peyton? Which one? Speak louder. The third law. Yes. Thank you. So for every action, there's an equal and opposite reaction. So what is the action? Someone's what on the log? Someone's walking on the log. So we can say person pushes backwards on log. What is the log doing? The log is pushing forwards on the person. Okay? So this is Newton's third law. All right? Person pushes on log. Oops. Log pushes on person. All right, equal and opposite reactions. You guys ever been to like the state fair and saw the log rolling contest that they have there? Where people will like get on top of logs and they'll try not to fall off and they'll spin them around. All right. Number 2. Heavier football players tend to play on the front line. Why is this? Which law? Which one? The second law, okay? Because, and really, you also could make an argument for the first law, and we'll give a reason for that. Generally, more mass means it's going to be easier to generate more what? Force. More force. Okay? So you could make an argument for the second law. Why could you make an argument for the first law also? What is Newton's first law? Inertia. Law of inertia. So things that have more mass, remember, as mass increases, so does inertia. So it's harder to move a larger object. Okay? So I would say Newton's first and second law here could potentially apply. So F equals ma and more inertia. All right. Many automobile passengers have suffered neck injuries when struck by cars from behind. How does Newton's law of inertia apply here, and how do headrests help to guard against this type of injury? What do you think? Zoe? Well, it tells you what law it is. It tells you that it's Newton's law of inertia, which is the first law. But why is it the first law? Kyle?
Because like when they're moving, they get hit from behind, it stops.
Well, generally, the problem here is the person's not moving initially. But when they get hit from behind, what does it cause the car to do? Causes the car to lurch forward, but what is your head doing? It wants to stay where it was. So your head is at rest, and it wants to stay at rest. Okay? So headrests, what they do is they help to keep your head from snapping backwards if somebody were to hit you from behind. like a stoplight or something like that. So your head is at rest. And it wants to stay at rest. So this is Newton's first law. All right. Number 4, suppose you place a ball in the middle of a wagon and then accelerate the wagon forward. Describe the motion of the ball relative to the ground and the wagon. You guys ever done this before? You set a ball inside of a movable object, and what happens if you move the wagon? If you move the wagon forward, what does the ball do inside the wagon?
It goes backwards.
It goes backwards. Now, is the ball actually going backwards?
Yeah.
It's actually not. So, it's going backwards in the wagon, but with its position relative to the earth, it's actually staying put. So the wagon actually moves forward. Like if this is your ball and this is your wagon, so the wagon moves forward, but the ball stays where it was. So it looks like it's moving backward, but actually it's the wagon that is moving forward. Now, what if you move the wagon backwards? What does the ball look like it's doing? It looked like it's moving forward. But again, in actuality, it's actually staying where it was. It's actually just the wagon that is moving backwards in that case, which gives the appearance that the ball is moving. So we described this motion. Now, what law is this?
First law.
That's Newton's first law, okay? Because the ball has inertia. Okay? So the ball is at rest. It wants to stay at rest. Okay? Now, if you pull the wagon forward enough, it's going to hit the back of the wagon, and then the ball is going to start moving forward. But while it's still within the parameters of the wagon and not touching the walls of the inside of it, it's actually not moving relative to the earth. It's actually the wagon that is moving. So you can put the ball wants to stay at rest. All right. Now, number 5. How many of you guys have ever been paintballing before?
So fun.
A few of you. Yeah. All right. Suppose you are standing on a skateboard, okay? And you shoot a paintball gun at your friend. Which direction relative to your friend will you move? Explain this. What do you think? Think backwards? Why do you think backwards?
Because
Right. Okay. You are basically, the gun is kind of attached to you, the paintball gun. So if you shoot your friend and the paintball gun exerts force forwards, then that means that the paintball is going to exert force on you backwards. So you are going to move away from your friend. Which law is this? Right, Newton's third law. For every action, there's an equal and opposite reaction. So, gun exerts force on paintball. Paintball exerts force on the gun. How many of you guys have ever shot a real gun before? Okay. So whether it was a handgun or shotgun, rifle, whatever, there's always a recoil that you get when you shoot a gun. So especially if you shoot like a really powerful gun, like a shotgun, like a 12 gauge shotgun or something like that, it's going to recoil really hard because it exerts a force on the bullet, okay, moving forwards, but the bullet is going to exert force backwards in the same manner. All right, number 6. 2 closed containers look the same, but one is packed with lead and the other with a few feathers. How could you determine which had more mass if you and the containers were orbiting in a weightless condition in outer space? What do you think? How could you determine which had more mass if you and the containers were orbiting in a weightless condition in outer space? Any ideas? What do you think, Kyle?
When you're talking about like hammer would throw it, maybe throw it farther.
All right, so that's a possibility. So yesterday we talked about, if you're stuck in space away from your space shuttle and you have nothing with you but a hammer, you could throw the hammer and the hammer would actually exert some force on you and push you back towards the ship. Well, in this case, which one is going to exert more force on you if you try to throw it? The lead or the feathers? The lead. So that's one way that you could actually test which one has more mass, is by throwing it, and whichever one causes you to accelerate farther and faster in the backwards direction, that would be the one that has the lead in it. Now, what law is this? This is Newton's second law. All right? F equals ma. All right, now, number 7. If you are sitting in a bus that is traveling along a straight level road at 100 kilometers per hour, you are traveling at 100 kilometers per hour too. If you hold an apple over your head, how fast is it moving relative to the road? So how fast is the apple moving relative to the road? It's also going 100 kilometers per hour. It's in the same bus relative to the road. It's also going 100 kilometers per hour. Now, relative to you, how fast is the apple going? 0. Remember we talked about this when we talked about setting your point of reference or your reference point, okay? So, like if you have 2 people that are riding in the car, they're not in motion with respect to each other, but they are in motion with respect to somebody sitting outside the car. So the apple would be technically going 0 kilometers per hour with respect to you inside the bus. All right, now, if you drop the apple, does it still have the same horizontal motion? All right, think about this. If you drop the apple inside the bus, is the apple going to fall straight down? With respect to the bus?
Oh, wait, yeah.
All right, I'm going to draw a picture real quick just to illustrate this scenario. All right. So let's say you have your bus and an apple. Okay. There's your bus. Bus is see-through. All right, here's you inside the bus. Okay? Now, here's your apple. Now, if you drop this apple and it is directly over top of this point on the bus, what point is it going to hit whenever you drop it? Is it going to hit this point or is it going to hit somewhere else?
It might hit a little bit on, it might be a little bit.
How fast is the bus going? It's going 100 kilometers per hour. How fast is the apple going?
100 kilometers.
It's also going 100 kilometers per hour. So technically, with respect to the bus, the apple and the bus really aren't in motion relative to each other. Okay? So this apple is going to fall straight down on the bus. But that's because the bus is in motion, so is the apple. So when you drop it, okay, it's going to fall straight down. You guys ever dropped anything in the car? It doesn't like fly into the back seat. All right, it just drops straight down because all those objects that are in the car, they're also moving at the same rate that the car is. So it's going to drop straight down. Now, here's the thing. Think about this. This is the road. With respect to the road, is the apple in motion?
Yes.
Yes. The road's not moving. The apple's going 100 kilometers per hour. Now, if you drop the apple right above this spot when the bus is in motion, where is the apple going to hit?
That spot, but the bus would be further away.
All right. I'm going to give you three options.
I just guessed
This is A, B, and C.
C.
How many of you think that the apple would hit at point B on the road? Just going to drop straight down. Like if you dropped it out the window of the bus, is it going to drop straight down? All right, how many of you think that it is going to be somewhere closer to A?
Oh, wait.
How many of you think it's going to be somewhere closer to B?
B.
Or sorry, C.
Oh.
C, my fault.
Of course, it's C.
Okay.
It's like, well,
Truth of the matter is,
Oh wait, no, because I'm.
it's actually going to be A.
Oh.
Well, that's what I was saying.
Okay?
Oh, how?
It's actually going to be A. All right, look.
Oh, because the bus was.
yeah.
Look at
It
this.
makes sense now.
I'll give you a scenario right here. Okay? I'm going to mark my location with this pin. All right? Right here on the floor. Okay? I'm going to walk holding this roll of tape. Okay? When I get to that pin, I'm going to drop the roll of tape and I want you guys to tell me where it hits. Got it?
Got it.
It's not
Okay.
accurate.
I couldn't see it.
All right, but where's it at with respect to the
Well, you,
pin?
you might have dropped, I think you like dropped it a little bit away. I don't think it was accurate.
Oh my god.
We'll do it one more time.
I'm telling you, you dropped it away.
I'm not dropping it late. Okay, it's right here. Okay, so it's actually going past it. When you think about it, it has forward motion. Why would the tape fall behind the pin? That's not going to happen. All right, there is going to be some air resistance, but it's not going to be enough to blow the
Well, if
thing
you're, like,
back
in a
completely
hurricane,
behind.
You're driving pretty slow, and then you drop it, it's like.
Well, you got to think about, you know, in a bus that's traveling 100 kilometers per hour, that's pretty fast. Now, this is something called projectile motion. All right? So, this is actually something that is traveling in motion, all right? And if you drop it, it's still traveling forward. It has an angled velocity towards the ground. So, what's going to happen is it's going to fall kind of in an arc pattern instead of just falling straight down like something that's not in motion. So, if you drop this out the window of the bus, it's actually going to land somewhere around here. Okay? All right. Now, number 8, last one.
Is number 7 like first, second, or third?
That one. Let me think. That would be first. Yeah. Because what does the apple have?
Mass.
Well, it does have mass, but the apple has inertia. All right. Objects in motion want to stay in motion. So the apple, if you drop it out the window, is going to want to continue in motion. So that's why it's going to continue moving somewhat forward until it hits the ground. And then the friction from the ground is going to stop the apple. All right. Number 8. A rocket fired from its launching pad not only picks up speed, but its acceleration increases significantly as firing continues. Why is this so? And the hint, 90% of the mass and weight of a newly launched rocket is fuel.
Can't see it.
Can't see what?
All of it.
Oh, sorry. All right.
I can't see it.
So what do you think? A rocket fired from its launching pad not only picks up speed, but its acceleration increases significantly as its firing continues. Why is this so?
It's not for the second one.
What do you think, Kyle?
Rocket pushes on the gas, gas pushes.
Yeah, so the rocket pushes on the gas pushes on the rocket. So we could say that this is which of Newton's laws? All right, so this is Newton's third law. What other law do you think could be applied here? Maddie, why do you say second?
I don't know. It says mass and weight.
All right, so think about this. Is the force being acted upon the rocket changing as it goes through the launch?
Oh, wow.
Not really. I mean, it's burning off the fuel. So once the fuel's gone, the rocket's going to be launched. But what is going down? What does it say right here? 90% of the mass and weight of a newly launched rocket is fuel. So what goes down as the rocket is launched?
The fuel.
It goes the mass, because you're burning off that fuel and losing that mass from the rocket. So if the same force is enacted on a lighter object, the acceleration is going to be greater. So you could also say that Newton's second law could apply here also, because F equals ma. So if the force is the same but the mass goes down, the acceleration is going to be greater. So it says it accelerates increasingly as the firing continues, and that's because the mass of the rocket actually is going down. All right. Anybody have any questions about any of these?